class. In this short video, I will talk about A-star search, which is the extra credit for PA4 final submission. This is not required, so if you want to try the extra credit, you can use this video as a reference. A-star search is a way for us to do a search from a source to a certain target. So it is slightly different from Dijkstra's, which gives you the shortest distance from a source to every other node in a graph. A-star is more focused on from a single source to a single target. But obviously, Dijkstra's can do this job, right? Except it's trying to do it for every vertex instead of a specific target. So how does A-star work? A comparison between Dijkstra's and A-star. Because Dijkstra is trying to optimize the distance via this triangle inequality, and we know that. And because it is trying to find the shortest distance from the source to every other vertex, right, all the way to Vn, for example, it's going to give you the shortest distance to all of them. And because of that, it kind of blindly try to do this without worrying too much, because Dijkstra's is meant to find the shortest distance to every vertex from the source. So it is kind of slower if all we care about is to go from S to T. This is the specific target. If S is San Diego, we say, well, what's the shortest distance from San Diego to San Jose, for example? What Dijkstra will do is not only can it find all the paths from San Diego to San Jose, it is also finding the shortest path from San Diego to San Francisco. Okay, so A-star try to make sure that we're really focused on this part instead of looking through all the other side branches as we go. So A-star is called an informed search, and it kind of inform our search algorithm via this thing called a heuristic. Okay, a heuristic function, in fact, is one of the trickiest things in practice, where you have to design a good heuristic function, because for heuristics, it is guaranteed that it can give you something, but it cannot guarantee the result will be optimal. So in other words, if you use the San Diego to San Jose as the example, if your heuristic is not designed properly, it will give you a distance from San Diego to San Jose. Okay, but it can't guarantee that this distance A-star find will be the optimal smallest distance. But there is a very nice property for A-star, because if the heuristic it is consistent and admissible, then A-star is guaranteed to give the optimal solution. So if we design our heuristic nicely, then A-star will just work very well, and it is in general faster than Dijkstra's. So what is consistent heuristic and what is admissible? Consistent heuristic, it is basically a kind of triangle inequality. If your heuristic basically satisfies the triangle inequality, admissible means you never overestimate. Those are the two properties. Later on, I'm going to show you one example, and hopefully this will make sense. But this is kind of what A-star is about. With a good heuristic, it is guaranteed for an optimal solution. So how does A-star work? Let's just do a quick review for Dijkstra's. We talked about this in class. Basically, for Dijkstra's, each node has, so for each node V, you're looking at, it has a distance, right? Has a previous, has a done. So initially distance is infinity, previous is -1, done is false, right? And as we go, we're trying to enforce the triangle inequality via this one, right? So if the distance, so if w dot dist and v dot dist plus the edge between them, if the triangle inequality is violated, you kind of fix the distance. You update the previous, and then you unqueue, right? So you unqueue the node. If a triangle inequality is fixed, and in the end, we find the shortest distance. So how is this different from A star? A star, in fact, is very, very similar to what Daisher gives, except now, in addition to updating the distance, we are also updating a heuristic. And we will unqueue not just the distance, but the distance plus the heuristic into the priority queue. So this is the major difference between A star and Daisher's. As you can see, it is very, very similar. And the purpose of this term in there, which is the heuristic term, is to guide us towards the goal. So because A star is trying to search what's the shortest path from a source to a destination. What this HV really does is to say, don't digress to other parts of the graph. Really try to focus on T. Okay. And what is a heuristic? So in the context of PA4 final summation, we're not using the actress graph. So what we're trying to say is for a vertex, this vertex has a heuristic function on it. So for this vertex, you can say it is the distance, in fact, the distance between V and the target. And you can use the Euclidean distance, which is Vx minus Tx square plus Vy minus Ty square. And if you know the xy coordinate of V and T, you can calculate this distance. And in fact, a very nice property of this Euclidean distance is it is both admissible and it is also consistent. So if you use this one as the heuristic, it is very easy for you to do this.